All right, so this project is going to break all the rules that we've kind of talked about before. So let's get at it. So I'd like to acknowledge my two co-authors for this, Dr. Adernisha Fraser and Dr. Hannah Nenig. They're with the College of Science and Engineering overall at University of Minnesota Duluth, and are kind of heading up this initiative across campus. And so they're in charge of a lot of the sort of overarching goals and data management and things like that. So my role in this is the project, concrete-based freshman design project. So let's get into it. I think I need to click in here first. Yeah, that'll do it. So just some background on where this initiative came from. So we, like probably many places, started with a 1-credit seminar style introduction to civil engineering. We discuss aspects of civil engineering profession, blah, 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 what does a civil engineer do? And within the last, I'd say, couple of years, we've had this initiative on campus known as SAIL, which is the Swenson Active and Innovative Learning Initiative, trying to incorporate more what we call authentic disciplinary experiences within the freshman experience. And so it's really the goals of this are to try to get students really engaged with their discipline and to start feeling like either a scientist or an engineer right when they come onto campus. So this is their first semester experience. So that first year class of 1 credit is now transformed into this 3-credit Intro to Civil Engineering course. So the objectives that we had for this was to incorporate a lot of processes about the design process, but not necessarily content-wise. And so you'll see why this course breaks the rules a little bit in some ways, but we start off, we want them to learn about brainstorming, so considering alternative designs, selecting one, developing solutions for that, and then going through an iterative process to be able to test and adapt their design as they learn new things throughout the semester. Probably one of our biggest objectives was just working on communication, both oral and written communication throughout the semester, so that's honestly, I would say, the largest objective that we were really trying to hit on in this, less so in the content side. And then taking a plan and then putting it into reality. So how can we do that? So understanding and implementing a plan, discussing changes as necessary if that needs to happen, which ties back into iteration. So I say project, but really we had 2 separate projects throughout the semester. So I was in charge of the concrete one, and then Dr. Nate Johnson was co-teaching this with me. He was in charge of the water project. So we'll discuss a little bit of the structure of how that works. Obviously, I'll be focusing on the concrete one. Their goal is to make a concrete bridge. It's a 3-foot span bridge. Concrete bridge goes there. So we have a very small loading device with just some hand jacks. Our goal is to carry about 5,000 pounds on that little tiny thing. There's an example of one of the bridges, but we'll see more of them later. They sometimes are kind of wonky looking things, but that's what we get when we do a freshman design. So, and then the water project, they're treating some groundwater for a variety of different use cases, and so different groups will have different specifications that they're trying to treat their water according to. So again, I'm not going to focus on that except in terms of how the projects are structured. So just a little bit of context before I go into the structure about what our class kind of looks like. So we're looking at about 65 students. We split them into 2 sections. So we're a lot smaller program than Urbana-Champaign, and that's sort of to our benefit, but we still have a decent amount of support with what we call learning assistants. They're undergrads that come in and sort of coach our students through the project. Coach is maybe a strong word. They can answer questions and other things like that. And then multiple faculty, myself and another faculty who are running the projects. We actually have a 3rd faculty that's kind of like running the overarching like professional development things. Anyway, so we have 5 stages to our project. So we have a brainstorming stage, what we call a testing development stage, our design plan stage where they're actually putting together design plans, and then they go into fabrication and testing. So that's the goal. And so we have what are called the design stage, the first 3, and then we have what's called the contractor stage or the contractor team stage, steps 4 and 5. We don't let the students pick their projects. That's a little bit different. So we assign half the students in one project to begin with and half the students in the other project to begin with. And they're essentially in team pairs. So one concrete team is going to be paired up with one water team, and they'll discuss with each other and present to each other like how they're going through the project. Now the twist and where this breaks all the rules is that the design team, the people who design the concrete bridge, do not build it. They take their design plans and they give it to their partner team who has to build their bridge. And the water treatment team gives their water treatment plans to the concrete team and they have to treat water. So this is where communication becomes extremely important. And all anarchy breaks loose basically at this point in the semester. So we let the students know that this is what they're getting into, just so we're aware. So the students are aware of what's going on, that there's a project swap and they're preparing for this. They're discussing with their team and with their partner team in advance to make sure that the swap is as seamless as possible, but it's not always as seamless as possible. So that's sort of the fun of the project, really. Yeah, so we follow no rules up in Duluth, apparently. So I'll focus on the concrete project and what we've done for that, because obviously this is ACI. So we'll divide the different teams up to satisfy different bridge objectives, just so we can get a little bit of variety in their design, so they're not all trying to do the same thing. So we'll have one team, for example, try to develop the lightest bridge, the stiffest bridge, the bridge that uses the least amount of cement, or the bridge that uses the least amount of steel, and then the shortest profile bridge, so just keeping it the smallest. And so they're not exactly graded on these, but it's a way to sort of encourage them, push them in slightly different directions, so they'll come up with different design ideas. And again, they're not explicitly graded, but we can check to see, it's like, hey, you were in charge of the lightest bridge. Is your bridge in fact lighter than the stiffest bridge, or the bridge that's incorporating the least amount of steel? Things like that. So we have a number of requirements that they need to meet, and then their objective function, if you will. So phase one, we start off just doing a concrete project brainstorming, so they need to come up with a preliminary design for their structure. And so we'll give them all the requirements. And so mainly what we're looking at here is if they can take a project and say, I need to develop a plan that meets these requirements. At this stage, we're not worried about how well it's going to work, and even in the last stage, we're not super worried about how well it's going to work. Really, it's just taking this project, or taking an idea and saying, okay, this is an idea that might meet the objectives, and will meet any restraints on our objectives. So for example, we'll have dimensional limits and things like that. So they'll sketch this thing out, and hopefully they'll have a reasonable idea. So first deliverable for this, they'll give an oral presentation of the preliminary design and how it satisfies the design requirements. Moving on, so they have to now develop their concrete mix. We don't tell them how to mix concrete. We give them basic lab safety. None of these students, well, some students will have a little bit of concrete mixing experience, and I say concrete pretty loosely. Technically, we're doing grout or mortar. So they're using sand, Portland cement, fly ash, water, and water reducer if they want in limited quantities, if they get sort of approval from us. But we tell them nothing about proportioning. Like I said, we just kind of turn them loose. And it actually works out very well. So they have about 1 month to go through their mix development. And in the first one, they'll kind of plot out something, and they'll be just adding water and other things, and they'll measure it out to get a kind of a feel for it's like, oh, okay, I probably need about this much water to get something that resembles concrete. And then they'll go through this process where after they've done after they've done the first one, they'll come up with a testing plan, which you can see here's a sample testing plan that one group provided. And we'll provide them a lot of the worksheets that sort of help them fill in the blanks. So we'll say, well, you need to come up with some sort of ratio of water to cement to your aggregate. So just very basic ratios. And that's sort of the main parameters that they're going to be tuning as they go through their mix development. Do we expect any students to come out with like really, really awesome mixes? No, we want them to have something that is workable, so you can make it and it can hold some load. Some of the mixes are incredible. I was very surprised. Some came out with, say, 8 KSI mortar mixes. Don't know how they did it, or if they looked online or something like that. Other ones could hold about maybe 500 psi. So very, very big range of what mixes were achieved. But the deliverable is their testing data sheets, and then their sort of final mix design that they're using to provide adequate strength and workability. And I say adequate loosely. As long as it's functional and you can mix it, like, we're good to go. All the teams did succeed at that, so excellent. Last stage for the design teams is now the design planning stage. So some teams went all out, and if they had some experience with AutoCAD, that was very helpful, but honestly, we didn't need that. Pretty much most people were just drawing figures on paper, just by hand, and that works just great. Within their design plan, this is, again, the plan that they're going to submit to their contractor team, and they need to have, they'll have an introductory memo, a bill of materials, so this is what you're going to need to procure. We provide all the materials to them in order to build this thing. Mix design and specifications, which is pretty much just a summary of what they just previously did. The bridge plans, and then a rough construction sequence. Now, the construction sequence was a little bit, we'll say, up in the air for a lot of teams. It depended on how well the two teams coordinated together, like their contractor's team with the design team. So sometimes we would have to step in as faculty or the learning assistants to kind of help guide the process along if the contractor teams got stuck. And there were a handful of teams, there was 2 teams. We had a total of, let me count them up, 10 teams that we divided our students into. And 2 of them struggled when they passed off the plans, and so there was just extra faculty time working through. It's like, okay, well, how do we address this rather specifically? But a lot of the designs, we were pretty hands-off and just kind of see what they did. All right, so at this point now they're meeting with the contractors. Well, they've met with the contractors long before that, but this is the pass-off stage. So they have to communicate their design, propose any changes, and consider the constructability of this thing. So now let's pass it off, and we're into the construction stage. Construction was largely done with foam, obviously their mortar mix, and then we used steel wire for reinforcement, which they could just bend into a variety of different shapes. They had, I think, about 10 pounds of steel wire that they could use for their bridge. No teams actually used that much of it. But you can see some of the forms here, and you know, filling it up with rebar, which worked well enough, and then filling up the concrete behind that. So a few more examples of kind of what we saw. Some teams definitely learned about form pressure, we will say. So this one over here, it was just like straight up and down foam sides, and that thing is like a foot wide. So actually, more exactly, it's a foot tall. They were casting on its side, and they were going to tip it over, and it was just blowing out the forms. So they braced it with a bunch of buckets with water in them, and that sort of solved the situation. But that's that's the sort of experience that we actually wanted to get, is these sort of unexpected things that students aren't really going to think about until you encounter it and you say, wow, that concrete puts a lot of pressure on that formwork. How do we keep that thing in place? And eventually, obviously, they'll pull it out of the formwork and somehow anchor them together. Some teams had better ways of doing that than others, and have some final bridges. So that was essentially their 4th deliverable, is the completed bridge. So finally, we get to go through the testing phase here. So testing, we just have, there's just 2 hydraulic jacks, basically just a hand jack. We give the students the privilege, I guess, or honor, I don't know what you want to call it. They get to break their own bridge, so they bump it up, so we don't have to worry about actuator safety or anything like that. And we got a couple catches to make sure the bridges fail. Yeah, and they all failed, so no bridge successfully carried 5,000 pounds. I think we're probably going to have to dial that back next year. But some got about 2,500, which I thought was pretty good. And one of the very nice things about this is the students could experience different failures in the concrete structures, and we would be discussing it as they went through it. So as you can see, I think the next, there's some sort of, I'll call this punching. They had put a hollow section to bridge here so that we could put the loading beam through that, and then we loaded that, and of course it's punching out the bottom where we're putting the load. The truss one over there, you can't probably tell, but there's a very large tension fracture in that one in the lower chord of your truss. A couple more examples. We can have some shear-like failures or flexure-like failures, and so it was really good just talking to the students with this as they broke their structures. Again, this wasn't necessarily, the class is not intended to teach content about, say, concrete structures or concrete design or even material design. We were really trying to get into the engineering process and the writing process. But at the same time, you know, some of these lessons, hopefully we're saying, hey, you remember what you did in freshman design, like we broke these things and some of them broke in, and I can even have the pictures for when that class came through. Some of these broke in tension versus shear, like what's the difference between these things, and so they already have some inkling of where they're going, even if they don't have the full story yet. Just some more examples of testing. Obviously when they go hard. These things are totally destroyed, and it was pretty fun. Anyway, so how do we assess outcomes for this? And before we talk about sort of the outcomes that we were assessing for this particular class, I do want to talk about grades a little bit. Basically, 0% of their grade was whether or not they actually succeeded at building a bridge that carried load. Like, that wasn't the point of any of this. A lot of it was on, you know, writing, making sure the deliverables were on time, making sure they responded to change orders if they had them, because holy cow, are there a lot of change orders. It's like, we're going to go build this thing. Like, there's not any steel here. What do we want to do? Guess we'll figure out how much steel to put there. And by figure out, like, they're not doing heavy calculations or anything like that. They're using intuition, essentially. And we could talk through that as faculty, but we didn't really give them an answer. So grading was essentially on writing type things, not whether or not they succeeded. But on our end, what we wanted to assess was self-efficacy. So are you feeling confident in your ability to do engineering? And so I apologize, like, all these are going to be framed in the context of science courses, because at the College of Science and Engineering level where this survey was distributed, everything was put in terms of science, and we had some discussion on whether or not that should be engineering as well. So if you like, you can scratch that and say engineering, but that's totally fine. So whether or not the students feel that like they've accomplished some sort of engineering task. And we had, so the all is all freshman experiences across the college. And then the CE is the ones that we got from our class, and we're hoping that by developing this project, we're getting good outcomes with that. And in terms of science self-efficacy, the top one, I feel confident in my ability to be successful in my science courses. They responded really well to that, and I think that was because we kind of just turned them loose and hoped for the best. So I think they felt prepared for dealing with other more complex labs in the future. Science communication, holy cow, we got ridiculous gains. The second one, I feel capable of communicating scientific knowledge to non-scientist community members. I don't know how we got a 50% increase on that, but that was apparently what we got. So it was really, really good, so we were really happy with that. But I think because the project forced them to actually engage with that fact and see somebody else's design, I think they got a really good appreciation for the fact that as engineers, we do have to communicate our designs effectively, and there's going to be a lot of back and forth communication in that handoff process between the design team and the contractor team. Science identity. Again, you could scratch this and say engineer instead of I consider myself a scientist, because that was the other one that we got really big gains on. I consider myself an engineer. Students really felt engaged with that. So we were really happy with the gains that the class was going. And we're going to do it again next year with some tweaks, make sure everything works out fine. But yeah, so conclusions, freshman projects are a thing. We had no background knowledge. Basically, these students don't know anything about engineering, frankly, and that's not a dig at them. They're freshmen. Like, they haven't gone through anything in the engineering program yet, but they can deliver on complicated projects, which impressed all of us, to be perfectly honest. They've learned a lot about communication and the importance of that. And they've also started to experience belonging within the engineering community so that they're already, as freshmen, engaged in a design process. So I thought it was really great. I think with that, I'll just say any questions.